Um, the title of my presentation is Device and Network-Centric Control and Modeling of Power Electronic Systems Networks. If you notice it, it's quite involved with the devices. So the concept I'm going to be talking about is device-centric control, and I'm going to tell you why. My presentation is a little bit long, so in places I'm going to be skipping through quickly, so please do not mind. So I just want to give a disclaimer about some of the patents. University of Illinois wants me to do that. My outline is going to be along these lines. I'm going to be talking very briefly about the role of control in traditional power electronic systems. And I'm going to be sometimes referring to them as the PES, so this is not Power Engineering Society, it's Power Electronic System. I'm going to be talking about overview of traditional power electronics control approach and what is beyond traditional power electronics control. That's going to be part of the focus. So the role of control in traditional power electronic systems. Regulation, whether it's a DC-DC converter of various kind, but we're trying to control output voltages, currents, power, whatever it is. Tracking, if you're doing inverters, AC to AC converters, DC to AC converters, PFCs, tracking is one of your goals. Could be startup, motor drives, resonance could be a major issue. So for the converters, startup is a big part of the transient. Could be the transient itself. For example, if you have got a cyclo, as you can see here, we're trying to kind of track the desired and actual, track the desired itself. Could be load sharing, could have multiple converters, and this is not limited to DC-DC converters, could be DC to AC, AC to DC, even AC to AC converters. So load sharing is important. Instead of achieving it using a single module, try to achieve it in a distributed. It could be energy source optimization, talking to somebody during the break, doing a lot of work in solar, so MPPT and others, and this is a major challenge, and you're not limited to a single panel. So a lot of work is going on in the renewable energy space. The thing many people do not understand, which is that MPPT is actually not limited to solar itself. I've done a lot of work in fuel cell, even in wind actually this is an issue. So it's sort of like, it's a renewable energy issue itself. Dynamic power management, which is another area that we're increasingly getting into. I think the power system people are quite familiar with it. So if I look at the role of control in traditional power electronic systems, the summary, regulation, tracking, startup, transient, load sharing, energy source optimization, power management. Okay, I might have left out a few, but in general, that's what it is. So overview of traditional power electronics control approaches. It's primarily analytical model based. So for example, if I've got a converter, typically 3 stages, you can see it here, power stage, modulator, or controller. Power stage could be any converter. For example, you're trying to maintain control the voltage. You feed it to a controller. I did not show the feedback here, but it's going to assume it is in here. But we need a modulator because the power stage in power electronics are discontinuous. And the way typically we do it, we start with, if you have a switching system which has bilinear or trilinear models. And then you do after you've done the power stage modeling, you look into the controller. Controller could be dynamic feedback controller. Typically that's what we use in power electronics, PID and all of these are dynamic feedback controller. That means that you're using states other than the power stage itself, but it's not limited to linear. And then you have the modulator, which as I said, it is taking a smooth continuous signal and creating a discontinuous signal like shown here, which you're familiar with it. This is just a single embodiment. The goal here is to solve a transcendental equation to get the switching instant here. Now we do not realize that because we just do it experimentally or simulator does it for us. It's actually a difficult process. And when we piece all of these things together, then we get different types of model. You could have a switching model like shown here. This is a hybrid representation. It looks like a linear differential equation. In some sense it is, but it actually is not because it's a piecewise linear differential equation. So it's a nonlinear in that sense. And then the thing is, you can converted into a map. Sometimes we call it a discrete model in power electronics. This is not a single, it's called a multi-value differential equation or set value differential equation. This is a nonlinear map. It can go to higher bandwidths basically, so to say. And then you have the state space average model, and there are different embodiments of state space average, what you call average model. The difference here is it's a single differential equation which is nonlinear. Typically we just say dependent on the duty cycle. So if you look at the pictorial representation, for same average, you've got the average model. The discrete model kind of looks like the same, but if you look at it, it basically has discrete points, and which is sort of the nonlinear map. And then if you have a switching model, it's a multi-scale dynamics. So the thing is, a part of my presentation, I'm going to be showing you some of the things that we could do more in controls, because I've been actually working in controls for a while now. And the device perspective more of in the last 15 or 20 years, almost did my second PhD in semiconductor device. It gives you a totally different perspective. But what I've been actually looking at in power electronics over the several years, the papers that are coming in, that's sort of going more and more lateral. You know, and then the other thing is we seem to be not going back and looking at who actually did things originally, because the more you go into it, then you can see the thing is some of the things we do actually scientifically has been done before. For example, averaging is often credited to Middlebrook and Chook, but actually the fundamental work was done several years back. And Alexei Fedorov-Filippov, I mean, this is the first book that I actually studied during my PhD, differential equation with discontinuous right-hand side. I mean, this is a very, very difficult book mathematically to read, about 300, 400, but it's just full of maths. But he actually has outlined what Chook actually called like an averaging it. And it's no coincidence, the thing is, Chook actually did not have any solution for DCM averaging it, because Filippov did it based on convex optimization. It only applies to what we call CCM. But this work predates our work by several years. In terms of the control and stabilization of average response in traditionally, well, we kind of started average model because we like it. We don't want to deal with discontinuity, even though the switching system is entirely discontinuous. We typically go for small signal analysis, and generally we are limited here and here. The general approach is take the average model, linearize it, do a frequency domain analysis and tuning, and then do a testing under simulation, typically for transient testing. And it is just not the academic community, even industry does it as well. Rest of there are a bunch of other theories which are not used. These are extremely powerful theories. There are people working on it as well, but somehow it does not make the mainstream. It is primarily single scale and slow scale control. So here is an example of the converter, and I'm just showing a simple gate drive circuit here. If you take the FFT, you can see that the dark line here is the average response. If you see the actual response, it's not a smooth, it's basically a piecewise continuous type of signal. And if you look at the FFT at the bottom, you can see the slow scale here, and the fast scale is completely eliminated. What is the fast scale? Fast scale is basically your carrier, and then you could have the sidebands, and you got the super harmonics. We are kind of limited here. Off late, there has been a little bit of a work in the area of grid connection, primarily due to the PLL, and as far as you're trying to do self-synchronization, it's probably going into, but it's still in this zone. Robustness is ensured typically in small signal sense, which means that power electronics converters are nonlinear, but we seem to be focusing on the nominal equilibrium solution, even though you could have other equilibrium. So if you're trying to do large signal response-based controller and things like that, you need to be aware of it. So when you do small signal analysis and then you go for step response, okay, sometimes you may be aware of it, but you're not doing the design based on that. You're kind of focused here. So modulation is typically not an integral part of control synthesis in power electronics. So here is an example of 3 average responses of the controller, which is typically fed to the modulator, and the type of the carriers are different. So you got ramps, you know, both ways, and then basically you got a triangular response, same average, and you can see the switching states evolve differently. In other words, the switching sequences are different. So what you're observing is that for the same average command, different modulation scheme yield different time evolution of switching states. So the time evolution of switching state is a switching sequence. So if you have a device working in hard saturation, your switching states are 2, 0 and 1, but switching sequence is different. That's where the time comes in. So this results in different Pascal frequency responses. As you can see it here, the simplest possible example, the switching sequences are different even though the average is the same. So if you keep on doing the average modeling, that's what you're getting. Primarily communication bereft control. Number one, we have been doing a lot of work on group control method. So the whole idea is, okay, we don't want to do communication. And this is something really interesting to me because generally speaking, this is well proven in control systems. So the thing is, you cannot actually work with ideally decentralized system. When we just say the thing is, what we typically mean that there is no data communication, all right? Many people have done the thing is there is no communication, but you are actually communicating, for example, over the power lines, okay? So Droop is basically one of that. And then the newer version of that is the DC to AC or the AC to DC or even the AC to AC version, the multi-phase version of it. So I've shown an illustration here, which is more and more coming into the microwave. And so decentralized control of power injection guided by self-synchronization of inverters. Okay, but the general idea is coming from the same thing. This is DC and this is time invariant, this is time varying. So my daughter basically when she joined her undergraduate at Harvard, like, you know, in the first semester she's taking a course on, she's actually doing molecular and cellular biology, did not like engineering, I guess. So she actually was taking a course on nonlinear systems, first semester, on mathematical biology. And she actually told me a problem, and that problem got me interested. The thing is, it's really about fireflies, how they synchronize it. So many people in power electronics, I don't know how many of you know it, the first work in this area was actually done by Harvard professor, Professor Art Winfrey. Actually, the guy who gets some of the credit is Kuramoto, but the work was done by Professor Art Winfrey. And I said late because he died. And I think probably hardly anybody in power electronics even know that he is the pioneer work. He actually spent his entire life actually developing this technique. So it's very important for us to basically know the perspective. And here is the first paper. This is the original work by Professor Winfrey, the basis of ongoing work, as I said, on synchronism. As you can see, it does not come from power electronics. Biological rhythms and behavior of population of coupled oscillators by Professor Art Winfrey. And he showed in his lifetime work, subsequent scientific work has demonstrated that without coordination, stability of such coupled systems cannot necessarily be guaranteed. This is proven mathematically. Sensing is time-driven and guided by Nyquist criteria. In other words, if your highest sampling frequency is F1, you're typically going at 2F1 or higher. And the same thing with F2 and F3. In other words, higher the frequency, higher the sampling rate. That seems to be the trend. Security is assumed to be assured. That means the thing is we've got power stage, sensing, communication, control. I give you an example. We seem to be thinking that these links are completely assured. Okay, these links are intentional, could be non-intentional disruptions. We are more used to the non-intentional disruption, but intentional disruption is going to be the future, what we sometimes call cybersecurity. So overview of traditional power electronics control approaches, primarily analytical model-based, mathematical. Okay, control and stabilization of average response, primarily single scale and or slow scale control. Robustness ensured typically in small signal sense. Modulation is typically not an integral part of control synthesis. Primarily communication bereft control. And sensing is time driven and guided by Nyquist criteria. And security is assumed to be assured. That is what power electronics is today. So what is beyond traditional power electronics control? I work in control. I mean, a part of me is I do a lot of work, like, you know, which I call like bread and butter type of work, a lot of devices and things like that. But part of me is basically scientific. I'd like to explore. I mean, we professors really have a job we can do for 30, 40 years. So we have the luxury to actually think about 10, 15 years from now. You could be flat wrong, but it is worth a try. What is traditional? What is beyond traditional power electronic systems control? So one of the ideas that I've been pursuing is switching sequence-based control, and I'm going to call it SBC. So it controls the time evolution of the switching sequences of a power electronic system. When I got into devices, I really understood the thing is the role of device basically in power electronics. We of course knew it. And the thing is that many people, when they say I'm controlling power electronic system, they will typically say voltage, power, frequency. These are control objectives. What you're really controlling in a power electronic system is the device. That is it. You take the device away from power electronics. That is the core aspect of it. And Alan basically said, I mean, it's presentation after presentation. It's centered around the device. Achieves optimality using a union of stabilizing sequences. And I'm going to show you that a little bit. Integrates control and modulation. So there must be at least 1,000 theses on modulation. You don't need to do that anymore because if you change the way you actually approach the modeling. And so note, like, MPC, unlike SBC, controls switching states while the switching sequence evolves. This is the first paper on MPC, by the way, and this is not by Rawlings. Generalized Predictive Control, Part 1, the basic algorithm. This is by Clark, a British professor, Mohtad and Tufts. And I've not really seen anybody actually even referring to this guy. And he actually did the first pioneering work in MPC. Why do we need a device perspective? Because I said switching sequence. So why do you need a device perspective control of power electronics system? Because all power electronics systems comprise semiconductor devices. The efficiency of a power electronic system depends significantly on the conduction and switching losses of these devices. Conductive and radiative noise and input-output distortion of a PES depends on how these devices are switched. Reliability of a power electronic system depends, among other issues, how its devices are triggered. And the bandwidth of a power electronic system depends how these devices are activated. Well, if it is switching based, everything that looks sensible, for example, rational, then let's do a reality check. Simple converter, buck converter doing a voltage mode control. And so here is a converter. I didn't tell you what it is. So we're trying to control the voltage. We feed it back, compare with the reference, some compensator, okay, whatever you want to choose. We generate a control, which is typically a duty cycle. And then we compare with this modulator here. Okay. And the reason we do that one is because this MOSFET here is operating in hard saturation and it does not understand this language. It understands this language, so you use a modulator. The moment you use a modulator, you set the sequence. Every modulator basically sets the sequence. The sequence that we use for the converter does not come from the converter, it comes from the modulator. We are forcing what the sequence the converter is going to be using it, but all the knowledge is in the converter itself. Rather than looking here, we're looking here. So this is the conventional PES control design approach. Start with a switching power electronic system average model, which literally gets rid of all the switching effects, and then continuous control and modulation. Because you realize the system was discontinuous to begin with, you have to end there. So device switching effects are completely eliminated, and the modulation is predetermined, not an integral part of control design. That is one of the reasons people are just endlessly working on modulation after modulation of modulation. You don't need to actually do that. So what's the problem with eliminating switching dynamics in an average model? So I go back to the same figure that I showed you. And I told you at that time the thing is, focus is on the slow scale. This is the scale you're eliminating. By the way, if you do switching modeling or discontinuous modeling, you do multi-scale. It's not limited here. But if you eliminate this, what do you eliminate? Fast scale accounts for switching loss, noise, device DVDT and DIDT stress, and control bandwidth. If you remember from Alan's presentation, all of these things you're actually highlighting have become extremely important, especially with wide bandgap devices. So the question really is, can controls do something about it? The answer is absolutely yes. So what is the problem with modulation, not an integral part? I already talked about it, so I'm going to skip this. But the main idea there was that for the same average command, the switching sequences are going to be different, and they make a huge difference. So SBC versus conventional control, I've already talked about it. Slow scale, fixed switching sequence, depends on the modulation. This is the pictorial. So you got the power stage that you're trying to regulate, measurements, feed it to a controller, modulation, discontinuous feedback signal. So you got a converter layer, switching control layer, hardware layer. In a new PES type of control approach, you start with the same system, which is switching, and you just do not get rid of the switching effect. You model it exactly the way it is. Discontinuous model or hybrid model, and then you basically create the switching sequence. You just don't need a modulator. So multi-scale with multiple feasible switching sequences. The switching sequences is up to you. You tell me what you want, and the thing is, as long as the converter can actually support the sequences, I can hop around among the sequences. It does not have to be limited by the modulation. So you do not really have a simplified controller. In terms of the control synthesis, the conventional versus the SBC, you start with PS model for both. Here you use average model, we use discontinuous model. Stability analysis, typically body plots, Nyquist, but in this case, you determine a set of feasible switching sequences. Why a sudden change in approach? Because you're dealing with discontinuous model. If you have a function y equals to absolute value of x, and I ask you, what's the value of y when x is 0? You right away will tell me the answer is y equals to 0. If you type in MATLAB, x equals to 0, y equals to absolute value, it will give you y equals to 0. Actually, at x equals to 0, y is undefined. The only way you can actually find it out what is the value of y in an absolute function x is by using limits. It's called right hand and left hand limits. If you apply that, then you can actually get the answer. It does not come automatically. The controller designed to achieve desired performance, phase margin, bandwidth, performance constraints cannot be directly included. Here, determine a subset of reachable switching sequences from the set of feasible switching sequences. Find out what is feasible, then create a subset, which is called a reachable sequence, and performance constraint included in cost function of optimization problem. In other words, whatever you're trying to optimize, you just said it could be single or it could be multiple objectives. Selection of modulating functions, predetermined modulator, typically depends on your experience, especially in motor drives. I've done a lot of work on it. We used to use controllers with multiple space vector modulations. We can hop around. Here you determine a union of optimal reachable switching sequences that yields desired PS performance. No predefined modulation is necessary. So you start with a discontinuous model, determine the feasible sequence, create a subset of reachable sequence, stabilizing sequences, and then use this one to actually create our optimality. And this is sort of a pictorial version of the same thing. This is one embodiment of offline and online. If you want to speed things up, right now we're looking at about a megahertz speed, some cases 5 megahertz type of converter trying to implement this. As you know, megahertz is a microsecond. So you can start with a discontinuous model, and it could be wide bandgap or NBG, meaning narrow bandgap. That means silicon, gallium arsenide, and all of these things. And the optimal performance control is here, but the reachable sequences kind of come in from here, and then feed the optimal switching sequences to the converter, and you can sense it, or you can use estimation as well. The first paper on switching sequence-based stability, which is the core aspect of it. This is the central aspect of it. Was actually published in 2010 by us, and took 5 years to theoretically prove and experimentally validate for multiple power converters. I mean, we did it converters after converters after converter, not limited to DC-DC converter, but all sorts of time varying converters for multiple power converters before published in IEEE Transaction Power Electronics. So I'm really thankful to my PhD students who at least were patient, because we're getting frustrated by this one. It took so much time. It shows for the first time that the core behavior of any power converter are governed by fundamental switching sequences. We're just been looking at the wrong place for control. The control actually is in the converter. The converter tells you all the story. It's sort of like guiding a student. You know, the thing is, when you guide a student, the capability has to be in the student. The job of the advisor is really to identify the potential and guide it in the right direction. So you've got an objective, okay, but guide it. If the student does not have the potential, there's not really much of a hope there. Extension of SBC to PS networks. I'm not going to go a whole lot in it, but we have done that a little while back. So the thing is, if you have microgrid, at that time when I did some of the work there, we just did not know what to call it. Like, you know, sometimes we'll call it homogeneous network, because the thing is all the nodes are similar. So today we call multiple inverters. In networks, that is called homogeneous network. Why homogeneous? Because all the nodes basically have the same functionality. Microgrid is under networks is called heterogeneous networks, because a node may have different functionality. Okay. So you could have a centralized control approach to this extension of SBC to networks, or you could have a decentralized approach. If you do a decentralized approach, we actually did it in cyber layers. We did not even know there is some field is going to be evolving called cyber physical system. And the thing is, you can break the central model or the monolithic model, and you can actually partition it. When you partition it, what happens, which is that you're never going to partition it in a completely decoupled way. So we got coupling terms here. And so the thing is, when you're doing group method and others, basically you're dealing with the coupling, trying to kind of maintain it within a constraints, let's just say. But in communication, you can actually deal with it in a different way. And then I don't have to go too much into it, but the key difference in the control approach really comes in the information processing aspect of it. Okay, but rest of the things kind of remaining similar, except in the hybrid dynamical model. If you have a standalone system, you don't deal with the delay as much. So this will become functional hybrid model. That means it will have delay in it. So the first paper on joint framework for PS and communication work was joint optimization of control performance and network resource utilization. Homogeneous, if you notice it, homogeneous power networks. That means all the inverters that we do, that actually classifies under that one. So PS network model is analytical, communication network model algorithm or coding based. What is the problem? The problem is the enhanced delay, or the another thing is enhanced delay deteriorates PS network performance, but enhances ability of communication network to operate close to network capacity. If you have a communication network, the first thing you have to know is what is the network capacity? What is the maximum data rate you can support? So we had these two major challenges. PS network model, like our system, is analytical, but the communication network, they don't talk that language. It is either code or algorithm driven. And then what you're finding is that if you increase the delay, control performance deteriorates, but if you increase the delay, it helps the communication network. How do you actually resolve this issue? So how can one solve a joint optimization problem, solution to this difficult problem that has direct implication on PS network scalability has been addressed. This was in 2010. So the step one on this SBC, as I said, the main issue was that the number of sequences explodes. So what we found out is that there are certain behavioral characteristics of all power electronic systems. Number one is complementary switching functions. So you could have a boost converter, which you have two switches, and the switches are operating in a complementary way. If you know the state of one, you know the state of the other one. Redundant switching states, if you've got a full bridge converters, you can see here the bottom two switches and the top two switches are on. In terms of the output voltage, it's the same. It does not affect the stability. It affects the control performance, not the stability. You could have repetitive switching sequences. For the same average, how you actually generate the sequence, okay, it's not making the difference here. And then the final outcome was the total number of feasible sequences for any converter, okay, is this simple expression, which can be done by somebody even who has graduated from high school. The N is the number of switching functions, W is the number of redundant switching states, and P, 2 is for CCM, and 3 is for DCM. So here is an illustrative example of a parallel converter, parallel DC-DC converter here. It has two switching functions because generally the two switches are complementary here. So I'm saying two switching functions. This is the logic table. And then if you look at, if you apply the simple maths, the total number of switching sequences is actually 15. I don't have the time to work it out, but we actually hand worked it out, and we found out that it actually comes out 4 plus 6 plus 4 plus 1. It's actually 15 sequences. By the way, you can generate millions of sequences, but these are the 15 switching sequences which are fundamental. What do you mean by fundamental? When you look at the particle theory, for example, what is a fundamental particle? An electron is a fundamental particle. Fundamental means what cannot be broken down. And if you look at the neutron, it's not a fundamental particle anymore because you can break it down into quarks. So these fundamental sequences mean this governs everything about this particular power electronic system. You can create mutated sequences, but all evolve from here. The step 2 is a discontinuous model, and we just basically wrote it in an error coordinates because it helps with the stability analysis. And our analysis basically included time delay as well, and this is distributed time delay. That means you can apply straight away to network control. The step 3 is reachable switching sequence. As I mentioned, we have found out the feasible sequence. We want to find out which of them is going to be reachable, that is stabilizing sequence. If you don't have any delay, the steps are pretty simple. You start with a composite Lyapunov function. It is a standard Lyapunov function, but this is composite. That means you apply for each switching state of a sequence. You pick up a sequence, any feasible sequence, it has multiple switching states. Create a composite Lyapunov function corresponding to each switching state. And then this is the standard Lyapunov stability concept. And then you solve an LMI. If you solve this LMI and you can demonstrate the P is positive definite, then that's it. That switching sequence is a reachable switching sequence. Okay. Everything else here is known from the power stage. It just looks mathematically that, but it is not really complex. If you have a time delayed system, that LMI becomes a little bit larger than that, but everything here is known except P. P is the one you try to determine. Today, this can be done very easily in MATLAB. There are so many LMI tools. In fact, we have gone beyond LMI using sum of squares basically tools. So when we did this one for asymptotic, people just, what about sliding mode? Okay, so this is sliding mode convergence. So as you know, in sliding mode, you could have orthogonal, you could have a non-orthogonal. Okay, so sliding mode, the difference here is in asymptotic system, like if you start with an n-dimensional system, you end with an n-dimensional system when you converge to the origin. In a sliding mode, you converge to a reduced order manifold, and then on the manifold, you stabilize it. And we actually demonstrated you can easily apply the theory. Step 1, reachability of the individual sliding surfaces or sliding planes. Step 2 is reachability of the sliding manifold. And the step 3 is convergence on the sliding manifold. So here is an example for the same converter that I showed you, and you can see it here. I'm varying the input voltage, and I'm looking at the reachability of this converter. Reachability meaning if you start with any arbitrary initial condition, how do you know the thing is it is going to converge to the desired goal, the desired design objective, let's just say. And you can see as you vary the input voltage here, you can see the dark lines here. This basically shows that the converter is going to be reachable. But the moment you come in here, the thing is it's unreachable. In other words, the thing is it's not going to be doing switching. How do you know a converter is going to switch the way you intended to switch? You just thought it is going to do that way. And it is telling you it is not even going to switch properly. In fact, it may not switch at all. So if it does not switch, well, in that case, how can you actually average? Averaging cannot be done on a single number. Averaging requires 2 or more numbers. We're doing averaging because we're saying it is an on and off. Well, if there is not going to be an on and off, then there cannot be an average model. Interesting thing here is what I'm trying to show here is that even though this region shows that the converter is going to be reachable, but we can even go into it and we can see the thing is part of the convergence is sliding mode and part of the convergence is asymptotic. Many people have told me the thing is it's kind of interesting, these people working on sliding mode controller, I can get the same performance using PID controller. The reason is a sliding mode controller is designed for sliding mode convergence all the time, but we are showing here a simple PID controller can also exhibit sliding mode convergence, but it is not designed for sliding mode convergence all the time. And the step 4 is the optimal selection of the reachable switching sequences. It's pretty simple, predict and optimize. What are you predicting? How long you're going to be applying the switching sequence? And the thing is that's a time horizon, and you allocate it among the switching states. And you do it using a 3-part way, which is basically you have the cost function, you got the constraints, and you got the models. We don't have the time to go into the detail, but if you know these 3, which is pretty easy, you can actually determine, you choose a switching sequence, reachable sequence, determine the time you're going to be applying it, and how you're going to be allocate the time among the switching states of the sequence. So let's look at some of the case illustrations. Multiple DC-DC converter for VRM applications. I actually started this work during a PhD, but the thing is, during my work at the university, and I applied it to some of Intel's applications. And then the idea really came from, like, so original work was conceived by me because I was so bored, like doing my PhD, I wanted to go from US to India. And the thing is, the flight used to take 24 hours. And I was thinking, man, like if I go to a suborbit, like quickly, and move at 200,000 miles an hour, and then basically drop to India, that'll be quick, right? And the thing is, that's why I actually got the idea of control outside the boundary layer, that means outside the Earth, and the control inside the boundary layer when you're actually switching it. And that was the first paper on it. And so here is shown that there is an experimental proof of it, that this is Intel's 50 megahertz per second VRM, and you can see it here that without using this SBC, we are able to control the response of the output voltage just below the reference. This is a very, very hard problem in VRM because you can see it 50 megahertz per second. Today this number is at least 20x higher. And it only comes down to like, a couple of switching cycles in here. You can apply it to 3-phase inverters as well. And you can see it here, this is a standard controller, the red one, and this is the SBC. And as you can see that after the transient here, SBC really does not care about the duty cycle has to be within, because there is no concept of duty cycle. And the thing is, it responds fairly fast, and the thing is, the steady state matches with the state-of-the-art linear controller. You can apply it to pulsating loads also. Navy came to us, they were interested in applying this to pulsating loads. So if you got a pulsating load, it typically has a magnitude, frequency, and duty cycle. And so the thing is, at that time, the prevalent response was going with an RMS. And what we demonstrated here is the RMS is really not the way to go. You have to create a reachable surface, which is encompassed by these 3 things: perturbation frequency, perturbation magnitude, and the allowable duty cycle. What matters is that what is the height of your disturbance, what is the duty cycle, and what's the frequency. So as long as this inverter is operating in this reachable surface, the system is going to be fine. You can apply to multiple parallel converters, in this case parallel rectifiers. I've been doing a lot of work with ONR. So you can see it here, SBC versus a linear controller. Transient steady state response is fine, but you look at the transient response, the SBC actually recovers fairly quickly. You can apply to, this is a patent we have based on a switchable bus for a fuel cell vehicle application. So between a switchable bus between the battery and the fuel cell. So the idea there is multiple modules that is connected to a switchable bus to the battery and the fuel cell, and then there's an application load. The question is, how many modules would you use? Okay, this is not a choice that you make offline, you have to make this thing online. That people do it. This is called the dynamic optimization. The question is, as you hop around the number of modules, how do you ensure, because let's say you got 2 modules are active, you want to bring in 2 more. The 2 that are coming in, they're actually coming in from cold. Or if you're going to be taking module out, you're changing the overall model of the system. And we actually applied SBC in here because the difference here is that instead of switches, we're switching the module itself. And by doing so, we can actually make the efficiency much flatter compared to the traditional approach. We can apply it to solar microinverters here, pretty simple microinverters that we got a patent on, and it's got 4 low-side devices right here. And the picture that I would like to concentrate here is the efficiency as a function of the voltage gain. This is using our conventional originally that we applied. And then what we realize that if you do some smart switching as the SBC, you can actually make the efficiency a lot better. Some other cases the efficiency is significantly better. You can apply it to solid state transformers. I've been doing a lot of work on high frequency links. So high frequency link is especially challenging because you're trying to minimize this transform, but you've got bunches of these devices here. So if you could do something about their operation and efficiency, that'll be great. But here, if you look at this particular picture, the thing is we're applying multi-objective. As I mentioned, the optimization of the control does not have to be single objective. So here, for example, we're doing only voltage regulation, controlling the output voltage, for example. But here we're doing voltage regulation and switching loss regulation. This is in milliseconds, this is in sub-microseconds. And we can do it MPPT also, which is going to be tens of seconds. And you can see for both of these cases, with the grid connected or standard, if you can see the improvement in the switching loss reduction is pretty significant. And I've been giving some presentation with, and I did not really know Tobias from ABB, and we were actually shocked. He's been working on drives, that how much of a significant improvement he also found in 3-level inverter drives. If you look at the transient response here using SBC, that you don't see an overshoot whatsoever. If you see the standard, this is state-of-the-art type of controller. There's a bit of an overshoot there. Why is it this? Because this is predefined sequence. This is hopping around. This can actually choose other sequences. And by the way, this is 1 order difference. This is 10 to the power minus of 4, this is 10 to the power minus of 3. This is a new one. Just have a paper submitted. We are going to second round of revision. We're doing gallium nitride work, and we can actually eliminate the dead time in gallium nitride inverters altogether using this kind of switching. And I'm showing you an example here. This is the one with the dead time, and this is the one without the dead time. A 32% reduction under 0 power factor condition. This is really, really difficult. Unity power factor is not that difficult. 0 power factor is tough, right? And we can actually eliminate 32%. Same converter. How you switch really matters. I believe this is the first paper which eliminates dead time in CAN devices. Now I'm going to talk a little bit about the transition control. But before I do that, let me just give you the perspective. In a switching sequence-based control, we're relying on the switching states of the devices, which are 0 or 1. What we are not controlling the transition between the switching states. What we are controlling the duration of the states. And there is one thing. And the second thing is, even though the states are 0 and 1, but you could create multiple sequences, and that's what we're actually controlling as well. But in a switching transition control, our focus is on the control, the transition between 0 and 1. That means on and off and off and on. This is extremely fast control. Control the system performance parameters, switching loss, DVDT, DIDT, and EM noise emission. Because that edge is where all the problem is, or the problems are emerging of a power electronic system by controlling the device transition dynamics. Applicable for majority and minority carrier devices. Majority carrier devices basically meaning MOSFETs, for instance. Okay. If you're talking about minority carrier devices, BJTs, IGBTs, thyristors, where holes and electrons play the role. And this is where I really help with my devices background. Not limited to active gate control. Many people think the thing is transition control is AG. It's not. STC is much beyond active gate control. Realizable using electrical and optical excitation. Today we are doing electrical. Actually, my undergraduate students are doing electrical. But we already done the optical excitation. I believe the optics, even though it is expensive right now, this is the future. You saw that multiple times. What is the issue that is coming up? Crosstalk, right? Optics is basically the carrier of optical wave or EM wave is photons. Photons are charge neutral. So here is a simple example. I got a MOSFET. I just replaced the picture of the MOSFET with the 3 capacitors here. This is your CGS, CGD, and CDS. As you're familiar with, these are the typical Miller capacitance of a MOSFET. And the typical gate drive is you create a pulsating signal, you have a resistance here. This RC time constant dictates how fast your device is going to be turning on. So what I'm showing it here, that if you could actually modulate this particular resistance, you can actually modulate the RC time constant. The question is, how do you do that one? There are different ways. But one of the ways we did it, we basically had a bipolar device, and we could control its optical excitation. So I'm going to show you in this simple illustration here how the drain to source voltage changes as I control the optical excitation. So this is basically the VDS across the MOSFET, and this is the intensity of my optical wave, which is controlling this resistance. So you can see the thing is, as I vary the optical intensity that I'm applying to this device here, you can see the VDS is basically changing. So this is just a cartoon. Now we can do this thing dynamically. We actually done it a few years back, but now we're doing really, really sophisticated control on this aspect. And this is basically the first paper on it. So the breakthrough paper was optically activated gate control for power electronics, published in 2011. Took about 5 years to prove and experimentally validate, and almost a second PhD semiconductor devices. Device is so expensive, but the thing is, I'm worth it, because the thing is, it was really a lot of brain tickling and etc. But the money was a big issue, but it's worth it because the results are really amazing. So once you get the idea, then the thing is, okay, let's try it. Okay, so here is, for example, a power semiconductor device whose transition dynamics I want to control. So you got like a couple of bipolar devices here, and the thing is, this can be done by LEDs or you can do it by laser. We chose lasers. So for example, you got on laser and off laser. On laser, you can control the intensity. As you control the intensity, you control the conductivity of these devices. If you control the conductivity, you control the charging and the discharging of this particular MOSFET. And this is basically a device we have to make. So this hybrid device is the one. So you can see the optical devices here, and you can see the gallium arsenide optical devices here, and the silicon carbide, the power semiconductor devices basically in here. This is a hybrid device, but we have to make these devices, and it's fairly expensive. And this is our first generation. We're just kind of starting from scratch and everything. We did actually the testing of the devices in here, sitting on the hot plate and things like that. You can see a lot of instrumentation required to test it, because this technology did not even exist. I had to use some of the driving technology that existed. Like for example, an $8,000 basically for a programmable driver. Today we have brought down the cost to below $5. So here is some experiment results here. So for example, in this case, you can see the MOSFET. So if you're familiar with the MOSFET, MOSFET typically goes to a threshold voltage. That's why the channel turns on. Then there is a Miller region. During this time, the CGD is discharging, and after that, it basically reaches to your desired gate voltage. So the trick is, the thing is, can you actually modulate this Miller region itself? And so what this result really shows, that we are able to modulate the Miller region. That means how much time the MOSFET spends in the Miller region by controlling the intensity of the laser that is actually firing the bipolar, the triggering device. So modulation of the Miller plateau width in gate voltage dynamics of power MOSFET with varying optical power level. And you can see the parametric results here, the rise time versus the fall time. Tiny little variation in the optical device is leading to a significant deviation in the rise time and the fall time. As you know, this is where your DVDT and DIDT is. So what's the goal there? The goal there is how device control leads to PS control. So this is my power electronic system. I want to control its efficiency. I want to control its stress, DVDT, DIDT stress. I want to control the noise emission. This is at systems level. But what I'm controlling is this tiny, tiny little optical devices which goes and controls the power devices. So you start here. You tell me what you want, and I'm going to trigger these tiny little optical devices. As I said, can be done electrically also, but we chose optical. Optics gives you significant advantage. So for example, here I'm controlling the optical intensity for the on and the off optical trigger power transistor, which goes and controls the on-state resistance, the rise time and fall time, and the delay. It goes and controls the switching dynamics of the power semiconductor device. We have done it in almost every conceivable device, majority and minority carrier, both silicon carbide as well as gallium nitride. And this device, as you control the main device, it goes and controls the power electronic system. I showed you the example for a single switch. It can be done for multiple switches. So by controlling the intensity of these tiny optical devices, one can control system level performance of a power electronic system. So the whole dream of controlling an entire system at a device level. So once that is done, let's do a little bit at a power electronics level, a very simple buck converter with a majority carrier device MOSFET. Now we know how to actually do this one, so we put it together. This is our first generation. You can see the assistant professor basically working with hardly any money. This is our second generation. Now we are well beyond that, but a pretty big jump, and we actually made the hybrid device. This is a stage where I was actually trying to figure it out. How do you actually make a device? We use a device, making one is a different thing. So here is the converter efficiency as a function of optical power. If you look at it, the optical power variation is not really a whole lot, but if you look at the efficiency difference, same converter, tiny little modulation, it's making that much of a difference in the efficiency. If you talk about DVDT and the DIDT here, so this is turn off, turn on, this is turn off, turn on, DIDT here. You can actually vary the DIDT. You can look at it, this is pretty significant large number, tiny little variation in the triggering devices. This makes a huge difference. As you know that if you try to turn the device on fast, your switching loss is going to be reduced, but you're going to mess it up with the stress and the EMI. So if you could dynamically control the edge, you could perhaps achieve both. What about the electromagnetic emission? I think Alan talked about it. It really is here. That's one of the issues, right? Edge here, right? So for example, if you got a converter and its electromagnetic spectrum is this, and you do not like it, you want to suppress particular, you can actually do that one. All you have to tell me, what is the spectrum that you want, and I can actually modulate the device accordingly so you can get the desired spectrum. Now we are doing things for the last 2-3 years, something even beyond that, because the thing is, as you go for smaller and smaller scale, totally different physics basically evolves. Now we're doing quantum control. So this controls the flow of the electrons itself. And it is very, very interesting because when you get into the control of the flow of subatomic particles, sensing becomes totally different thing because Heisenberg's uncertainty kicks in. How do you control something you cannot even see? Example, enhancing electrically induced thermal reliability, dynamically manipulating carrier mobility. So if you're not familiar with it, these are the fundamental properties of the materials. And the lifetime, right? Lifetime is which is dictating your speed. Control the flow of or interaction with photons. So this is something I'm very interested. For example, how do you actually make an inverter, okay, direct AC to DC to AC without inverter? It actually can be done. We're actually looking into these things pretty closely. It can be done without an inverter altogether. Multi-scale control, co-synthesis of SBC and STC, I talked about both of them in near future, further synthesis with quantum control. So control realization at disparate time scales. Redundancies could be exploited towards realization of multi-objective power electronic system performance optimization. So the goal is multi-control, controlling a system at the device level, and if possible, even deeper than that. So co-synthesis of STC and SBC. Here is my blue is the power electronic system. It has power semiconductor devices, which I'm controlling using my triggering optical devices. And this is basically my control. My control is transition control and switching sequence-based control. Switching sequence-based control controls the evolution of the switching states, does not do anything with the transition. The transition control goes and controls the edges. Now how do I reconcile these two? We basically come up with an idea with two-dimensional modulation. You can control the weight which is coming from here, but the height actually tells you how fast the device is going to be turning on. You feed this signal to a driver, which feeds it to a couple laser drives, and then optical links feeds it to an optically triggered power transistor. This is our first, as far as I know, first in the world. This is actually can do both. This is discrete. Now we're doing optical. I understand there are other people working integrated circuits also. We are aware of that one. But this is first photonic integrated circuits we are actually looking into right now. This is a discrete realization. And this is a 150 ampere module. Right now, I could not bring the results, but we are at the verge of getting about a 2 kV SIC, all optical SIC realization. Hopefully in the near future I can show you. This is device at 150 amperes, and this is a close-up of this one. And here is the testing, we're actually doing it, and the package device is right in here. So the dream is that don't be limited to state regulation, voltage control, frequency control, and things like that. Power electronics, unlike traditional power system, it's a multi-scale system. I think it's a complete shame. The thing is we're using power electronics control just focusing on the single scale because it suits power system. It's a multi-scale system. How about basically thinking much better than that? How do I basically do voltage regulation or frequency injection while I'm minimizing the losses, for example? I mean, we're doing MPPT because it's much slower scale, and you can go way more than that. You can maintain that scale, but you can optimize many other scales. So the research challenge for multi-scale control is real-time, single or multi-objective optimization spread over disparate time scales. Some of the time scales are sub-microseconds. If you look at GaN devices, 10 nanoseconds, 12 nanoseconds. When the device is turning on, you have to control that edge. This is going to be sub-nanosecond speed control. Is there or do we need a unified modeling approach? Okay. The device that we think, average model does not include switching effect. If you do SBC, that says on and off. You do transition control, you need device physics. You do quantum control, that does not mean anything. Now you're going completely different. So do you need a unified modeling approach? How do you ensure multi-scale stability? If you're going to be doing multi-scale control, where is the multi-scale stability theory? How do we deal with non-convex optimization? Convex optimization is easy. Non-convex optimization is really hard. How do you break speed accuracy trade-off barrier? Finite computation resources. If I had to use a 200 cluster HPC to do this problem, that's easy. Doing it using a single processor, that's difficult. Do we need to follow multi-core NOC approach, that is network on chip approach? Ultra high speed sensing. How can we control a system whose observed dynamics is slower than the system dynamics? Addressing non-intentional and intentional uncertainties and disturbances. This is a real hard problem. So what is beyond traditional power electronics network control? This is what currently control is. Legacy grid, fundamental scale at 60 or 50 hertz. This is where we are and going. Yeah. And this is all power converters, like Alan said. So multi-scale power systems need to resolve conflicts, but need to exploit advantages. So scalability in spatial dimension without compromising granularity in temporal scales. That's the key. Let's not forget the identity of the power electronics in trying to meet power system needs for grid application. Power electronics is a totally different beast. Want to think bigger? Here is what we have today. DC grid, right? HVDC, MVDC. Here is traditional AC grid. This is what people have worked on, high frequency link, so matrix converters and others. How about coded asynchronous multi high frequency power transfer? In other words, your power that you're actually sending is actually discretized and coded. Okay? If you're talking about security, you can actually code it. You can discretize power. There is no reason the power cannot be discretized. And if power can be discretized, therefore it itself can be coded. It can be coded for efficiency, we have demonstrated that, but it can be also coded for efficiency and bunches of different things. So this is traditional power. This is what we can actually do today. And here is a proof of that. Here is a standard power line communication. Here is a power line signal and the data is injected on it, conventional PLC. Here is our patented technique, for example, a high frequency power transfer followed by high frequency data transfer, sequential co-transmission of power and data. You see, power is discrete. It does not have to be continuous. So it's called Boolean transfer, sequential co-transmission of discrete data and discrete as synchronous power. There is absolutely no reason the power transfer has to be synchronous. I understand there is a legacy reason, but if it is not legacy, there is absolutely no reason it has to be synchronous. Okay, so sequential co-transmission of discrete and power. Yeah, I'm going to just wrap it up quickly. And this is basically the proof. This is work going on in our IEEE transactions, and you can see the thing. This is a proof of this particular one, and you can actually see the power and the data are transmitted basically sequentially in here, and this is a pictorial representation. This is the first work on discrete power and the data. For the lack of time, basically I'm going to speed it up, but information and need-centric control coordination, we need to move away from conventional sampling to compressive sampling. Need to move away from information, not data-centric, so we need to go towards information and not data-centric control and coordination. Instead of time-driven communication, I think it's time to look into event-driven communication or even self-triggered communication. Event-driven, you do it when you need it, not like all the time. Communication protocols are not designed to support controls. Instead of an OSI model, you can actually look into need-based communication type of approach. You can see the simplicity in the control architecture. I'm going to skip this, the different system identification needs for the lack of time. I'm going to skip this one as well. So the research challenges with power electronic network control. How does one achieve global versus local dynamic stabilization and control while ensuring modularity and without losing the core power electronic identity? How does one determine the information content or authenticity of a nominal set in real time? How does one synthesize an optimal framework in a multi-dimensional control communication sensing space that maximizes data compression and reliability? And the methodology for nonlinear system identification of a generalized hybrid dynamical model. Power electronics is a hybrid system in the presence of stochastic latencies and information network capacity. That's my final slide. So overall conclusion is the control of power electronic system network is all about controlling the devices distributed in space or time to meet system or network objectives. Diffusion of this control information across space and time requires radically new approaches to communication, sensing, and computation to complement power electronics actuation. Multi-scale control of power electronic systems and network can yield unprecedented capabilities that we have barely touched upon due to our continuing tunnel vision of mono or sole flow scale control. Synthesis of a control at a new scale requires fundamentally different understanding of physics and mathematics and how they relate to overall power electronic dynamics. The last one, and probably the most important one, as applied as power electronic system is, if you kill the science in power electronics, we'll probably kill the spirit of fundamentally new innovation and we'll lose the innovative next generation. Thank you very much. I apologize for taking a little bit more time.